Welcome to lecture number 35 for ECE 461 Control Systems, Bode Plots. Now at this point we're going to switch gears. For all the previous lectures, we've been looking at the time domain. Basically use root locus techniques to specify the closed loop poles to give you good step response. And with step responses, we specify the closed loop system in terms of settling time, percent overshoot, frequency of oscillation. A different way of looking at the system is from the frequency domain. Here, the plant is a filter. Let us go to j omega, apply a sine wave in and get a sine wave out, but it has a gain and phase shift, i.e. it's a filter. If I close the feedback loop around this system, sometimes the filter works well, sometimes it works poorly. If I have a poor system, add a pre-filter, k of j omega, that warps the frequency response, turning a bad system into a good system. So that's a different way of looking at it. That's the approach we'll be looking at for the rest of the semester. Now, this technique actually predates root locus and goes all the way back to the 1930s and World War II. Now, the problem they were looking at back then is primarily twofold. One, if I have a vacuum tube amplifier, vacuum tube amplifiers have a gain which varies with frequency, and that causes distortion. To get rid of that distortion, I'd like to use feedback to make the closed loop gain a constant like 1. The problem they ran into is that sometimes when you close the feedback loop, you get a very good amplifier. Sometimes it just screeches. Kind of like at a rock concert, if there's too much feedback, you just have this horrible screeching noise. That's typical with amplifiers too. They tend to oscillate if you have too much gain. So they're looking at how do you analyze the frequency response of a filter and maybe add a pre-filter, K of S, to make a bad system behave like a good one. Another problem they were looking at is designing anti-aircraft guns back in World War II. Can apply a sine wave in, the anti-aircraft gun will respond. How do I close the feedback loop so that if I'm trying to track something like a German bomber flying over London, that I can hit it? So these primarily came from Bode, Nyquist, and Nichols, and some of their techniques are what we'll be looking at in the next couple of lectures. Now you might wonder which technique is better. That's really a matter of taste. You're probably going to like root locus techniques better than the frequency domain techniques. The main reason is that's what we cover first. Other faculty, for example, have looked at which techniques students prefer, and what they found is that whatever you present first in this course is the approach that people like. We used or presented root locus first, so you're probably going to like root locus better. Other faculty present the frequency domain techniques, the Bode, Nichols, Nyquist diagrams first, and people tend to like those best. They both work. We're presenting both techniques for completeness. Also, some systems are easier to analyze using root locus. Some systems are easier to analyze using frequency domain techniques. So really these are just tools. Use whatever tool works for you. Now starting out, we're looking at the frequency response of a plant, frequency response of g of j omega. The problem you run into is I've got three variables. I've got the frequency omega, I've got the gain at that frequency, g of j omega, and the phase shift, the angle of g. And it's hard to plot three variables on two-dimensional paper. So there's a couple different alternatives. A Bode plot plots frequency on the x-axis on a log scale, and the gain in dB. dB is the log of gain. So it's basically a log-log plot. A Nichols chart plots the phase on the x-axis and gain in dB on the y-axis. A Nyquist diagram plots the real part of the gain versus complex part. And the inverse Nyquist diagram is 1 over the gain, real versus complex. So those are just really kind of semantics. Really what I want to do is look at the frequency response of a system, and from that design a compensator. Now here we're going to start with Bode plots. Kind of recalling what we did initially, back at the start of the semester when we had a plant G of S, we looked at how to find the step response of a system given the transfer function. And we also looked at going the other way around. Given the transfer function, find the step response. And to do that, we looked at dominant poles, 2% settling times, percent overshoot, things like that. We're going to do the same thing here. From the frequency domain, given your transfer function g of s, find the frequency response. And going backwards, given the frequency response, what's the system? So that's what we'll be doing in this lecture. Basically, Bode plots, determining the Bode plot and using the Bode plot to find the system. A couple definitions to start with. The gain is just the magnitude of g of j omega. The gain at any frequency is a complex number. Its magnitude is the gain. dB is a log version of gain. dB is defined as 20 times the log base 10 of the magnitude of the gain. And gain, going backwards, is just 10 to the dB over 20. So, with those definitions, we can start looking at trying to determine or plot the Bode plot, determine the frequency response of a system given g of s. And we'll look at two approaches. One's numerical methods, i.e. MATLAB, and the second will be graphical methods. And this is probably easiest to explain through an example. So just for example, suppose I had the following system. I've got 2 zeros, 2 poles, and a gain up on top to 10. The simplest approach is to use MATLAB. One way is let s go to j omega, calculate the gain at each point, and plot it. This used to be a really bad solution because complex numbers are a pain on slide rules. Today with MATLAB, you don't really care. So just pick something like here. I'm going to pick 250 different frequencies between 0.1 and 1,000 radians per second. This notation is 10 to the minus 1 to 10 to the 3, the range, and how many data points. S is j omega, and g of s is the way you write it. It's 10 times s plus 100 divided by s plus 1 times s plus 10. And note I'm using the dot notation because this is a 250 by 1 column vector. I don't want to do matrix multiply. I want to do element by element multiplication and element by element division. The dB is just 20 times the log base 10 of the magnitude of g of s, and then plot on semi-log paper. So this is what the Bode plot looks like. And notice on log paper, the scaling goes 0.1, 0.2, 0.3, 1, 2, 3, 10, 20, 30, 100, 200, 300. And the magnitude in dB, this is actually log scale too because I took the log of the magnitude. This is what you get. That's the Bode plot for this transfer function. So that's the easy way to go. Let MATLAB do the work for you. Bode plots are kind of common, so we're going to write a function in MATLAB called Bode2. I'm going to pass g, the transfer function, and the frequency points, and it returns g of j omega. The way to do that is, first specify gw as the same dimensions as w, and then spin through the array. At each point, at each frequency, calculate g at that frequency, store it in gw. The calling sequence then would just be, here's my system g, here's frequency, calculate the gain versus frequency, and then plot frequency versus dB on semi-log paper. And you wind up with this graph. We'll be using this function quite a bit for the rest of the semester as well. That's the numerical solution. Graphical solution is the way we used to do it. Back in the days of slide rules, calculating complex numbers was really painful, so we didn't do it that way. Now with MATLAB, sure, you don't care. But we're going to cover the graphical solution because it offers better insight as to why the frequency response is as it is. And more importantly, if I want to add a compensator to change the frequency response, what do I have to do? Now, first note, if I have a gain of s to the n on log paper or on a Bode plot, that plots as a straight line. If I take this in dB, dB is 20 times log base 10 of the magnitude. Property of logarithms, a number to the n power is just n times the log. So the dB is 20n times the log base 10 of w. What that means is that I'm going to go up by 20 dB as frequency goes up by 10. So for example, if I have n is minus 2, or g of s is 1 over s squared, n is minus 2, I'm going to drop by 40 dB per decade. And that's what you see here. I drop by 40 dB as frequency goes up by 10, drop 40 dB as they go up by 10. That's a slope of minus 40 dB per decade. So next, suppose I had, next we'll do the Bode approximation. The Bode approximation says, given a term like s plus a, that's going to be roughly a when s is less than a, and s when s is bigger than a. What that does for you is, given the transfer function, I split it up into regions. When s is less than 1, s plus 100 is roughly 100, s plus 1 is roughly 1, s plus 10 is roughly 10. And I wind up with just 100s, a straight line on a Bode plot. When s is between 1 and 10, s plus 1 is s, this is 10, that's 100. I get 100, I get a straight line. Between 10 and 100, I get a straight line. Between bigger than 100, I get a straight line. So when I plot these, what I get are these red lines, the straight lines. G of s is just a constant, or what was it? 100s. Is 100s between 0.1 and 1. It's 100 between 1 and 10. 1000 over s, and then 10. And notice at the poles and the zeros, I have a corner. That's with the origin of the term corner frequency. Sometimes the pole is called the corner frequency because when you draw the straight line asymptotes, I get a corner right there. The actual frequency response will just approach these asymptotes. I'll start on this asymptote, and then go to the second asymptote, go to the third asymptote, and wind up back at the fourth asymptote. At the corners, I'm off by 3 dB. The reason for the 3 dB error is I'm approximating s plus 1 as either 1 or s. So at 1, I'm going to say s plus 1 is 1. It's actually the square root of 2. The magnitude of 1 plus j is square root of 2. Square root of 2 is 3 dB. So I'm off by 3 dB at the corners. If it's a pole, I'm 3 dB down. If it's a 0, I'm 3 dB up. So the way we used to draw the Bode plots is you draw the straight line approximations. Mark at the corner, I'm down 3 dB, so go from one asymptote, pass through this point, hit the second asymptote, pass through this point, go to the third asymptote, pass through this point, go to the fourth asymptote. And that's how we would draw the Bode plots. That's for real poles. If you have complex poles, it's about the same. The caveat though, if I have a complex pole, I have to have its complex conjugate. So if you had a complex pole, the slope's going to drop by 40 dB per decade, or 2 poles. In addition, the damping ratio tells you the gain at the corner. For example, if my pole's at 1, and I've got a damping ratio zeta, the gain at the corner is going to be s squared is j squared, which is minus 1. 1 and minus 1 cancel. It's just 1 over 2 zeta. So the gain of the corner tells you what the gain is. As an example, suppose I had this system. Plot the gain versus frequency. In MATLAB, I would just throw it in MATLAB and I get the blue curve. For a straight line approximation, what I would do is I've got 2 poles at 1, 2 poles at 10. As s goes to 0, I have s squared. So the gain starts increasing at 40 dB per decade. That's the s squared. At 1 radian per second, the slope drops by 40 dB per decade. Then at 10 radians per second, I drop another 40 dB per decade. That's the red lines. At this point, factor this out, the pole's at 60 degrees, cosine of 60 is 0.5, zeta is 0.5. The gain of the corner is 1 over 2 zeta, is 1, so I actually hit the corner right here. At this point, zeta is 0.25, so 1 over 2 zeta is 2, or 6 dB. So I'm going to go from this asymptote, hit a resonance, or go up 6 dB, and then approach the third asymptote. So that's how you would draw the Bode plot with complex poles. I'll also let you go the other way around. Suppose I went in the lab, measured the gain versus frequency, and got this curve. What's g of s? Well, the procedure is kind of going backwards. First, drawing the straight line asymptotes. Next, notice how many poles I have. Here I got the slope dropping by 40 dB per decade, so I've got 2 poles at 1. Slope drops another 40 dB per decade. I've got 2 poles at 10. To find the angle of the poles, I notice at this point I hit the pole, so I'm down 0 dB at the corner. That tells me that 1/2 zeta is 1, zeta is 0.5, or the pole is at 60 degrees. That's this guy. Over here, the gain at the corner is up 6 dB, or 2. 1/2 zeta is 2, zeta is 0.25, arc cosine is 75 degrees, so phi is 75 degrees. And then finally, to find the gain k, I've got the form of the compensator that sets the shape. Pick any point, doesn't matter which one you pick. Pick any point like 0.1, 3, 100. Match the gain at that point. So I've matched the gain at a point, matched the shape, I've matched g of s. And here what I picked was 0.1. At 0.1 the gain is minus 20 dB. This is g of s, the two have to match up, so k is 99.49. So that's kind of the procedure to find the transfer function. I'm going to go through one more example. If I have a gain versus frequency like this, find the transfer function. Now one approach is, it's pretty clear I've got an asymptote right here at 0 dB per decade. I've got a second asymptote right there at 80 dB per decade. So this system is fourth order. 80 over 20 is 4. I've got 4 poles. Also as a caveat, when you draw your asymptotes, they have to be multiples of 20 dB per decade. A single pole is 20 dB per decade. 10 dB is half a pole. Half a pole means half a derivative. I have no idea what half a derivative is. So you have to have integer numbers of derivatives. You have to have integer numbers of 20 dB per decade when you draw your lines. But anyway, this says I've got 4 poles right here. A single pole, if it's real, is down 3 dB. 4 poles are down 12 dB. This is down 22 dB. If I find zeta, I'm going to get a zeta bigger than 1, which is nonsense. Zeta is cosine of theta. I can't get a cosine bigger than 1. What that tells you is that I don't have a complex pole right here. I've actually got real poles. So I need a couple more asymptotes. So redrawing it, here's 0 dB per decade, then minus 20, minus 40, minus 60, minus 80. Those are my asymptotes. Where they hit is the corner frequency, that's a pole. So I've got a pole at 1.1, pole at 3.3, pole at 12, pole at 30. That gives me the shape. To find the gain, pick a point. Like at 0.1 radian per second, the gain is 12 dB. Find k, k is 52.25. Now note that with frequency domain techniques, I get all the poles, not just the dominant pole, so that's a real plus. This is actually a lot easier to do than some of the approaches with step responses. I just have to measure the gain versus frequency at a couple points, and given that, I can tell you what the transfer function is. So there's quite a few advantages for frequency domain techniques. The one caveat, a mistake I see a lot of students making, is on this graph, don't overdo it with the slopes. Like some people say this is flat, then plus 20 dB per decade, flat, minus 40, or minus 60, then minus 40. That doesn't actually work. If you have a hump like this, that's a resonance. I just have a single complex conjugate pair right here, and the angle tells the damping ratio, or the angle tells you the resonance. That's lecture number 35 for ECE 461, Bode Plots. And with that, you should be able to, given a system, draw its frequency response, or given the frequency response, find the system.